Welcome to part 2 of the video on the hypothalamic-Pituitary-Adrenal axis. Okay, so we are about to discuss then the synthesis of cortisol by the zona fasciculata cells from the precursor molecule, which is cholesterol. Okay, so let's actually begin this pathway then. So here is our molecule of cholesterol. So the first step then in the conversion of cholesterol to cortisol is to convert cholesterol into a molecule known as pregnenolone. So we're firstly going to convert cholesterol into pregnenolone, and ideally we would have had this all on one great big page, but never mind, it's not to be. So we'll do the first bit here, and then we'll have to probably go over onto the other side to do the final bit. So cholesterol is firstly going to be converted into a molecule known as pregnenolone. Now let me explain what is actually going to happen then to the cholesterol molecule to convert it into pregnenolone. You are now going to get rid of part of the side chain that comes off carbon number 17 here. What you're going to change this side chain into is just 2 carbons, where the first carbon that now comes off the carbon 17 now has a carbonyl group, is now a carbonyl group. So let me show you what the side chain is going to look like after the conversion has occurred. So this is what a molecule then of pregnenolone looks like. So it's still of course a steroid, in fact it's still a sterol. So here is ring A, here is the alcohol group coming off carbon number 3, here is ring B, like so. Here is the double bond between carbon 5 and carbon 6, the methyl group coming off carbon 10 there. Here is ring C, ring D here, the methyl group coming off carbon 13, and now this side chain coming off carbon 17, this is what it's going to look like. So here is carbon number 20, but now you've got a carbonyl group there, so double bound carbon number 20, you've got an oxygen, and then you've got a methyl group still coming off there, so there's carbon 21 there. Okay, so that is now what the side chain of pregnenolone, the side chain of carbon 17 is going to look like in a molecule of pregnenolone. And this is the first conversion that's going to occur in the zona fasciculata cells in the synthesis pathway for cortisol from cholesterol. So cholesterol is going to be turned into pregnenolone. Now what's the enzyme then inside the zona fasciculata cells that is going to catalyse this first conversion? Well, it's a very famous enzyme by the name of cholesterol sidechain cleavage enzyme. So cholesterol side chain cleavage, and for short, side chain cleavage is often just abbreviated down to SCC. So you might see this abbreviated down to cholesterol SCC, or more likely you'll see it written as P450 and then subscript SCC for side chain cleavage. Now the reason it's abbreviated down to that is because it is an example of a cytochrome P450 enzyme. So there's a very large family of important enzymes that are majorly expressed in the liver but can be expressed in other tissues, and then there's the cytochrome P450 enzymes, and the cholesterol side chain cleavage enzyme is an example of a cytochrome P450 enzyme, hence why we've got the P450 here referencing that fact. So if you ever see P450-SCC, that means the cholesterol side chain cleavage enzyme, which begins the first conversion. It converts cholesterol into pregnenolone. Oh, and by the way, this first conversion is the same first conversion that will happen in all of the layers of the adrenal cortex when you're producing whatever corticosteroid from that list that we've discussed. It's the standard conversion, and then the pregnenolone will go its different ways to make the different corticosteroids. Okay, so first conversion then, cholesterol is going to be converted into pregnenolone by the cholesterol side chain cleavage enzyme, which is going to be in the zona fasciculata cells. Next, we're going to convert pregnenolone eventually into something known as 17-hydroxyprogesterone. However, there are 2 different ways that you can actually get to 17-hydroxyprogesterone. You can either firstly convert pregnenolone into progesterone, or you can convert it into 17-hydroxypregnenolone. and both of those can then be converted to 17-hydroxyprogesterone. So I'm going to go through the first pathway first, and then we'll come back to the second pathway. It's just doing the same two conversions but in different orders. So we'll firstly go through the one where we firstly convert pregnenolone into the very famous hormone progesterone. So pregnenolone is now going to be converted into progesterone. Okay, and let me now draw you out then the structure of progesterone. So to convert pregnenolone into progesterone, we're going to now go to the opposite side of the molecule to make changes. We're going to change this alcohol group that comes off carbon-3 here into a carbonyl group. So, and we're also going to change the position of this double bond. So this is now what progesterone looks like compared to pregnenolone. So it's still going to be a steroid. It's no longer going to be a sterol because it's going to lose this alcohol group here. So we're going to have ring A here, ring B here. I have to go small to make sure I've got enough space here. Ring C, and ring D here. Haven't really got enough space to put this sidechain in it. Oh, sorry about this squeeze. So that's exactly the same as here. It hasn't changed. It's just a little bit squashed there. Okay, right. So now the things that have changed is we're going to move where this double bond is. It's going to now, instead of being between carbon-5 and carbon-6, it's going to be between carbon-4 and carbon-5. So just so that you can make sense of this isn't supposed to be an electronic mechanism or anything, but just so you can make sense of this, imagine breaking this double bond here, sending one electron back to carbon-5 and one back to carbon-6, then go to carbon-4 here and break one of the bonds between that carbon and the hydrogen atom that's bound to it. Send one electron back to the carbon and one back to the hydrogen. You can then form a bond between carbon-4 and carbon-5 by using the two electrons that each of them has. Carbon-4 has a spare electron, carbon-5 has a spare electron, and then you combine the hydrogen to carbon-6 here, and that's perfectly fine. So you've just moved the double bond over in that way. Now what you're going to do to the alcohol group that comes off carbon number 3 here, you're going to take away the hydrogens. You're going to oxidize this. So you're going to oxidize it to a carbonyl group, like so. So what you can imagine doing is taking the the hydrogen off the carbon number 3 and the hydrogen off the alcohol oxygen here. So break both of those bonds, give one electron back to each member. Then the oxygen and the carbon will have will have a free electron each. You can then form another bond between them, which is how you form that double bond there. And overall, this reaction will produce 2 hydrogen atoms, which will be why it's an oxidation reaction, and those can be accepted by some sort of electron carrier. Okay, so that's the conversion then of pregnenolone to progesterone, like so. And this is catalyzed by an enzyme known as 3-beta hydroxysteroid dehydrogenase, which is often abbreviated down to 3-beta HSD. So HSD here stands for hydroxy, that's the H, and then steroid, that's the S, and then dehydrogenase, that's the D. So 3-beta hydroxysteroid dehydrogenase, like so. Okay, right, so another enzyme inside, of course, the zona fasciculata cells. So we're going to convert pregnenolone to progesterone by this enzyme, 3-beta hydroxysteroid dehydrogenase. Then the next step, progesterone can be converted to 17-hydroxyprogesterone, and this is a very simple conversion. I mean, the name gives you exactly what's going to happen now. So the next molecule we're going to create is going to be 17-hydroxy, and ideally it would be all one word, but I haven't got space for this, so I'll have to put it on the next line. So 17-hydroxyprogesterone is going to be the next molecule along in this synthesis pathway. Okay, so what is going to be the difference then between progesterone and 17-hydroxyprogesterone? Well, we're just going to add an alcohol group onto carbon number 17. So carbon number 17 is, of course, this carbon. At present, look on this picture because it's bigger. At present, this carbon has 3 links to other carbons and therefore 1 link to a hydrogen atom. We're going to break that bond between this carbon and the hydrogen, and we're going to replace it with an alcohol group rather than a hydrogen. And that's how we're going to create 17-hydroxyprogesterone. So I'll just draw it out here. So here is ring A, like so. Here's the carbonyl group. There's the double bond between carbon 4 and carbon 5. Here is ring B, like so, no longer with the double bond between 6 and 7 there, or rather 5 and 6. Then we've got ring C here, the methyl group coming off carbon 13, and then ring D, like so. Put our side group coming off carbon number 17 here, and now we're also going to have an alcohol group coming off carbon 17 like that. Okay, so this is 17-hydroxyprogesterone, and this conversion of progesterone to 17-hydroxyprogesterone is catalyzed by an enzyme known as 17-alpha-hydroxylase. So this reaction is catalyzed by 17-alpha-hydroxylase enzyme. Right, so now what I want to talk about is the alternative way that you can convert pregnenolone to 17-hydroxyprogesterone. So there are two different orders that you can do these two conversions. You can either, as I say, do this conversion first, where you turn pregnenolone into progesterone, so this is catalyzed by the free beta hydroxysteroid dehydrogenase enzyme, and then you can do the conversion of progesterone to 17-hydroxyprogesterone by adding on the alcohol group onto carbon number 17, catalyzed by 17-alpha-hydroxylase, or you can swap these around. You can firstly change up here, and then after that change down here to get this molecule. Okay, so that's the second way in which you can convert this to this. And this will produce you 17-hydroxypregnenolone as an intermediate. So I just want to go through that alternative pathway. So unfortunately, as I say, we're now going to have to move on to the other side of the piece of paper. So I'll just copy a few of the molecules down so that we've got them here. So the one that I want to copy is pregnenolone. So let's just go over pregnenolone again. This never hurts to revise. So remember, pregnenolone, it's a sterol. So we've got the alcohol group still coming off carbon number 3 here. Here is carbon, here's ring B. Here is ring C here. We'll have the methyl group coming off carbon 10, the methyl group coming off carbon 13. And here is ring D, and then we've got the sidechain, this modified sidechain now coming off carbon 17. So this, I'll remind you, is the steroid or sterol pregnenolone. Okay, so this time what we're going to do is we're going to let 17-alpha-hydroxylase enzyme act first, and then we'll let 3-beta-hydroxysteroid dehydrogenase act second. So we're firstly going to add an alcohol group onto carbon 17. So exactly the same, take the hydrogen off carbon 17, stick an alcohol group on there instead. So what we'll end up with then is just pregnenolone with an additional alcohol group on. So here's ring A with the alcohol group of carbon 3 again. Here is ring B with our double bond between carbon 5 and carbon 6. Ring C, methyl group coming off carbon 10. Here is ring D, methyl group coming off carbon 13. And then our side group coming off carbon 17 up here. And now we'll have an alcohol group also coming off carbon 17. And this molecule is, of course, now 17-hydroxy, and this time I will be able to write it all as one great big word, pregnenolone. Okay, right, so now what we can do is we can convert 17-hydroxypregnenolone, this molecule, into 17-hydroxyprogesterone by letting the enzyme 3-beta-hydroxysteroid dehydrogenase work. So you can just do the two conversions to get pregnenolone into 17-hydroxyprogesterone in different orders is the message here. Okay, so this was catalyzed by 17-alpha-hydroxylase enzyme, which is in the zona fasciculata cells. Right, so now let's go over the second conversion just to make sure it's firmly in everyone's mind. So we can now convert 17-hydroxypregnenolone into 17-hydroxyprogesterone by making the changes that we did down here, and I'll remind you what those changes are. As I say, it never hurts to revise or go over something twice. Okay, so 17-hydroxyprogesterone. So the changes that we're going to make are going to be down here. So remember, we do two changes. We move where the double bond is. We move it from being between carbon 5 and carbon 6 to being between carbon 4 and carbon 5. And we'll also convert this alcohol group to a carbonyl group. So, putting this in, here is the A ring here. And now we've got a carbonyl group coming off carbon 3, we've got a double bond between carbon 4 and carbon 5. Then here we've got the B ring, which no longer has a double bond in it. Then we've got the methyl group coming off carbon 10, the C ring there, D ring, methyl group coming off carbon 13, and then our side chain up here coming off carbon 17, and also the alcohol group coming off carbon 17. So this is our picture of 17-hydroxyprogesterone. So to summarise, so far what we've done is we've converted cholesterol into pregnenolone by P450 sidechain cleavage enzyme. Then we overall wanted to convert pregnenolone into 17-hydroxyprogesterone. There were two options as to how you can do this. Either you can firstly let 3-beta-hydroxysteroid dehydrogenase, and in fact that's a good point, I didn't actually write that here, but this would be catalyzed by the 3-beta-hydroxysteroid dehydrogenase enzyme. Either you can let 3-beta-hydroxysteroid dehydrogenase work first and convert the pregnenolone into progesterone, and then you can do the 17-alpha-hydroxylase enzymes bit and convert the progesterone into 17-hydroxyprogesterone, or you can do it the other way around. So you can firstly let 17-alpha-hydroxylase work, converting pregnenolone into 17-hydroxypregnenolone, and then do the 3-beta-hydroxysteroid dehydrogenases part and convert the 17-hydroxypregnenolone into 17-hydroxyprogesterone. So both of those pathways will be occurring inside the zona fasciculata cells. So overall, so far, we have ended up with 17-hydroxyprogesterone, and we want to now see how this is going to be converted into cortisol. And don't worry, there are only two more steps now, one more intermediate that we need to learn. So, next, what is going to happen, and I'll use this space here, next it's going to be converted into a molecule known as 11-deoxycortisol. So that's reassuring. It has a name very much so related to cortisol, and a name that might just be one conversion away from cortisol, and indeed it is, so it's fine. So this is 11-deoxycortisol next up. So how are we going to convert then 17-hydroxyprogesterone into 11-deoxycortisol? Well, we're going to add on another alcohol group, and this is actually the running theme here. To convert cholesterol into cortisol, the main change that we're going to be doing is adding alcohol group after alcohol group after alcohol group, making it more and more polar. So it gets a greater and greater water solubility, although it still retains its lipid solubility overall, which is why you can't contain it inside vesicles in the way that you can, for instance, other hormone molecules. Okay, right, so 11-deoxycortisol, where are we going to add our next alcohol group? Well, I'll tell you the name of the enzyme that's going to perform the conversion, and that will give you a clue. So we're going to, the enzyme that is going to catalyze this is going to be called 21-hydroxylase, and that tells us everything we need to know. It's going to stick on an alcohol group onto carbon-21. So all we need to know is where is carbon-21, so that just requires you to remember the numberings of the carbons in this molecule. So remember, this was 17, this was 18, this was 19, 20, 21. So it's going to add an alcohol group onto carbon-21, which is up here. Now that carbon is currently a methyl group, so it's currently got 3 hydrogens coming off it. Just snap one of those off and stick an alcohol group there instead, and that's going to give us 11-deoxycortisol. So I'll draw this all out here. So, here is ring A, okay, I know you're probably getting fed up of me saying this now, but what else do you expect me to say? So here is ring A, here is the carbonyl group, here is the double bond between carbon 4 and carbon 5, which was produced by, remember, the 3-beta-hydroxysteroid dehydrogenase enzyme. Here is the B ring, here's the methyl group coming off carbon 10, here is the C ring, here is the D ring here, methyl group coming off carbon 13 there, and then we have our side chain coming off carbon 17 here, and now remember it's got a little bit more interesting. We're going to have an alcohol group in addition coming off carbon-21. So here's carbon-21, here's the alcohol group. Don't forget the alcohol group, or that also comes off carbon-17 there that was put in by 17-alpha-hydroxylase. Okay, so 21-hydroxylase has converted our 17-hydroxyprogesterone into 11-deoxycortisol, and we're getting very close now. All we need to do now is one more conversion to convert 11-deoxycortisol into our final steroid molecule, which is cortisol, the glucocorticoid that's going to be secreted into the bloodstream. So how do we do this final conversion then? we are going to quite simply put another alcohol group in, and where do you think it's going to be? Well, if this is 11-deoxycortisol, then it's cortisol without an oxygen coming off carbon 11 would be what I would read that into. So a good guess would be that we're going to put an alcohol group on carbon 11, and indeed that's exactly what we're going to do. So remember, where's carbon 11? This was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we went up to here to find 11. That was carbon 11. Okay, so we're just going to stick an alcohol group on there. So now let me draw out the final molecule here, and this final reaction is just going to be catalyzed by an enzyme known as 11-beta hydroxylase. So it's going to put an alcohol group onto carbon number 11. So underline its name in orange here. And now let me draw out the final star of the show, the final molecule here. So here is the ring A. Here we've got our double bond between carbon 4 and carbon 5, our carbonyl group coming off carbon 3 here, ring B here, with our methyl group still intact coming off carbon 10, ring C here, and finally ring C's been made a bit more interesting. We've now got an alcohol group coming off carbon 11 there, and ring D here, methyl group coming off carbon 13 there, and now here's our side chain, carbonyl group there, and then we'll have an alcohol group coming off carbon 21, and also don't forget the alcohol group coming off carbon 17. That is the final structure then of the steroid hormone that is cortisol, the glucocorticoid released by the zona fasciculata, produced and released by the zona fasciculata. And I have now shown you the synthetic pathway by which you convert cholesterol into cortisol. Now, if you don't remember this in 3 weeks, I hope that at least the message that cortisol is produced from cholesterol will remain in your mind. All of this excessive knowledge, yes, maybe you might not remember it in 3 weeks, but I hope that at least that fundamental concept that it's produced from cholesterol will still remain there. And that hopefully now seems a totally trivial fact compared to remembering the entire synthetic pathway. So, that's the synthetic pathway then by which you convert cholesterol into cortisol. So we're not going to talk about at the moment what controls the synthesis and secretion of cortisol by the cells of the zona fasciculata. As I say, we'll come on to that right at the end, the control of it all, the axis. At the moment we're just talking about what actually happens. So this is the cortisol. We've got it now. So what will now happen is it will be released from the zona fasciculata cells into the bloodstream. How then is it actually transported around the bloodstream? Now it is reasonably water-soluble, more water-soluble in a way than cholesterol because it's had all of the alcohol groups stuck onto it. However, still the best way to transport cortisol around the body is to have it bound to proteins that are in the bloodstream. That's another way in which often molecules that aren't particularly water-soluble can be transported around the bloodstream by binding to plasma proteins that are in the bloodstream. And indeed, this is what cortisol majorly does. So let me tell you the names of some of the proteins that cortisol is going to bind to in the blood. So this is what it's going to bind to in the blood. So, to be transported around the blood, it's going to bind to two major proteins. One, the major one, is cortisol-binding globulin. So this is a protein that is present in the blood, and which is one of its major roles is binding to cortisol molecules and allowing them therefore to be transported around the bloodstream. So cortisol binding globulin, often abbreviated down to CBG, and I might just draw a little picture of it here. So this box is going to represent cortisol binding globulin, and then here this can represent the little molecule of cortisol binding to it, and then this package here will now be transported around the blood, and at the peripheral sites where the cortisol is going to act, the cortisol can unload from the cortisol binding globulin and then go into the peripheral cells and have actions on those peripheral cells. So this is cortisol binding globulin outlined here in vivid pink and often abbreviated down to CBG. Oh, by the way, there is another name that is used for cortisol binding globulin. We've got the abbreviation, but now there's another name. It's also called transcortin. So any time you ever hear anyone referring to transcortin, that's just cortisol binding globulin, the protein in the blood which binds to and transports cortisol around the bloodstream. Another one that's important to know about, which transports all sorts of molecules around the bloodstream, is of course albumin. The easy answer, if ever you're stuck and someone's asking you what protein does a certain molecule bind to be transported around the bloodstream, your best guess is albumin. It transports so many different things that are barely water soluble around the bloodstream, so it's a one that's used all over the place, and cortisol is no exception. It's transported to some extent by albumin. But cortisol binding globulin is more important in the transport of cortisol than albumin, but some of the cortisol does indeed bind to albumin proteins in the bloodstream. So these are the major two proteins in the bloodstream which cortisol molecules can bind to, and then the complex of the cortisol molecule with the binding protein will then move around the bloodstream, and the cortisol can unload from the binding protein at the peripheral sites and then enter the peripheral cells. And we will talk about what it does in the peripheral cells in the next video. So far we have produced the cortisol, it's gone into the bloodstream, it's been transported around the bloodstream, and it's now in the peripheral cells, and we want to discuss how is it going to change the behavior of peripheral cells. So we'll discuss the glucocorticoid pathway, receptor pathway, in the next video, and then we'll talk about what are the effects that it will have on different tissues of the body. And as I say, we're not going to go through all of them. We will focus on the metabolic effects of cortisol and also the effects on the immune system, so anti-inflammatory and immunosuppressive actions.